Using nanomaterials and nanofabrication processes, it is important to process them into useful nanointermediates. This is due mainly to a fact that most of the added value from the nanotechnology is from the nanointermediates. For this, it is important to understand and learn about microelectromechanical and nanoelectromechanical systems, which are called as MEMS and NEMS, respectively. As introduced in previous slides, the process is started with nano or micro fabrication such as lithography, thin film technologies. Using these methods, it is important to prepare basic modules for the micro or nano systems such as cantilever, bridges, combs, pillars, coils, nozzles, and so on. By integrating the nano or micro modules, it is possible to prepare and integrate the MEMS and NEMS such as nanosensors, microactuators, and other functional structures. For your understanding, let's look at some popular microstructures in microsystem technologies. To build microsystem, we need to physically realize a variety of microstructures of different shapes, sizes, and materials depending on their purposes. So, we need to develop techniques that enable us to fabricate these structures. By top-down bulk micro-machining with numerical control, we can form hole, trench, or groove and membrane. By using surface micro-machining, we can prepare pillar, dam, cantilever, and bridge. You can see some examples for the modules or parts for the MEMS and NEMS in this slide. First, let's look at micro and nano sensors and actuators. Miniaturized devices that can measure a parameter of interest typically in non-electrical signal domain, and provide an electrical signal in response to the parameter measured. For example, as shown in the left figure, micro-pressure sensor can feel the mechanical pressure using piezoresistive pressure unit, which turns the mechanical stimuli into electrical signal. For the signal transition, there are two required units. The first one is sensing element for input pressure to physical movement translation, and the other one is transduction unit for physical movement to electrical signal translation. Miniaturized devices usually that convert one signal into action mechanical output. It can create a force to manipulate itself, other mechanical devices, or the surrounding environment to perform some useful function. As shown in the right figure, radio frequency MEMS switch can take input electrical signal as a form of time-dependent voltage and translate it into mechanical output form for the physical movement. Actually, the transduction mechanism in micro and nano devices are physical phenomenon that is responsible for transforming energy from one state to another. Here is a summarized table to understand the interconnected relationships for the various nano and micro systems. For example, the signal translation from thermal input to electrical output is thermoelectric sensors. It is possible to make more complicated signal transduction system. Let's think about a power sensor system which takes electrical input, turns the input into thermal signal, and outputs electrical signal. For this purpose, unknown AC input signal can be transported to a heating resistor which records sensing temperature, and then generated DC output signal that provides a similar power to the other resistor. We can classify the systems by some application fields. 1. Radio frequency MEMS. RF switches, variable capacitors, inductors, reconfigurable RF filters, antennas, RF resonators, etc. 2. Optical MEMS. Waveguides, micro-mirror array, scanner, micro-display, optical switches, cross-connectors, multiplexers, attenuators, etc. 3. Inertial MEMS. Gyroscopes, accelerometers, inertial switches, etc. 4. Bio-MEMS. Microfluidics, micro-total analysis system, drug delivery system, lab-on-a-chip, micro-valves/pumps, chemical sensors, etc. 5. Power MEMS. Micro-engine, micro-battery, energy harvesters, etc. Here is an example how NEMS and MEMS module can contribute to the preparation of useful systems such as miniaturized gyroscope for automobiles and smartphone. Acceleration can be translated into mechanical vibration or variation which can be turned into electrical signals. MEMS and NEMS with micro-cantilever can be used for biosensors. Here is a working principle. 1. Diffusion of vapor molecules into the polymer coated on the cantilevers. 2. Swelling of the polymer. 3. Bending of the cantilevers. 4. Optical detection of the displacement. With an array of cantilevers, it is possible to prepare a sensitive electric nose as shown in the upper right figure or ultra-sensitive scale for the detection of single virus mass as shown in the lower right figure. One of the most promising and advantageous systems based on the MEMS and NEMS for biological applications is microneedles. They employ an array of sharp micro or nanotubules, through which designated amount of drugs can be transported directly into the tissue or vascular network. MEMS and NEMS have been used widely for a variety of practical applications such as in automobiles. Actually, it is more and more important to integrate many of the sensors and actuators for autonomous automobiles such as Tesla. For example, MEMS and NEMS can miniaturize and distribute pressure sensors, mass flow sensors, gyro sensors, silicon nozzles, gas sensors, LiDAR, microscanners, microphones, and so on, in anywhere in the car. In this slide, you can find the practical applications of MEMS and NEMS for smartphone. For healthcare applications, MEMS and NEMS have much to do. In addition, as the demand for the wearable healthcare devices increase, MEMS and NEMS are required to be much more miniaturized and flexible for rollable and foldable environments. There are challenges for NEMS from MEMS. 1. Communicating signals from the nanoscale to the macroscopic world. 2. Understanding and controlling mesoscopic mechanics. 3. Developing methods for reproducible and routine nanofabrication. By overcoming these obstacles, NEMS will achieve some notable advances such as oscillators with resonance sensors for the detection of magnetic forces of a single spin, biomechanical forces, and adsorbed mass at pico or femtograms.